So previously we were looking at ways of calculating free energy, or delta G. We said that there are 3 ways to calculate delta G. The first was delta G is equal to delta H minus T delta S. The second way that we talked about was Hess's law. The third way that we can calculate delta G should look super familiar. We've already used this method to calculate delta H. We've already used this method to calculate delta S. So what we can do if we're given standard values for delta G is we can say that the delta G for our reaction is the sum of the moles of our products for G, the moles of our products times the G for our products minus the sum of the moles of our reactants times the G for our reactants. So that's what we're doing in example 9. Now I'm not going to solve the entire thing because, as I've said, we've done a lot of these problems, but just a reminder, I'm looking at moles of my products, so 2 CO2. I would find the value, negative 394, plus I've got 4 H2O. H2O is negative 229. So the moles of my products times the G of my products minus, so I've got 2 CH3OH, methanol, is negative 163, plus 3 times O2 is 0. So then I would just tally everything up. I'm not going to take the time to do it, but just a reminder, I can use this method for delta G, delta H, or delta S. So just a quick summary. These are the values we've been talking about in this chapter, and it's really important that you understand how they're different and how they're related. Delta H is going to be enthalpy. Positive tells me the reaction is endothermic. Negative, the reaction is exothermic. Exothermic is favored, but it does not mean the reaction is spontaneous. Delta S is entropy, our randomness, okay? Positive means we're becoming more random. Negative means we're less random. Positive randomness is favored, but again, it doesn't mean that the reaction is spontaneous. Delta G is my free energy. It determines whether or not my reaction is spontaneous or not. If I have a positive delta G, my reaction is not spontaneous. Negative delta G means my reaction is. Delta G depends on both delta H, delta S, as well as temperature. So, I wouldn't memorize this entire table. There's no real reason to. However, I would know that if my delta H is decreasing, my reaction is exothermic, and my delta S is increasing, my randomness is increasing, my reaction will be spontaneous always. I have more randomness, less energy, this reaction always goes. I would also know that if I have to put energy in to make my reaction go, it's endothermic, my randomness is decreasing, then this will never be spontaneous. This reaction will not go at any temperature, period. Okay? Now, everything that we've done so far is for standard temperatures and pressure. What if we have non-standard conditions? Okay? So if we have non-standard conditions, this should say delta G, can be calculated from this equation. Now, if we look, some of these things should be familiar. Here is our free energy at standard conditions. R we've talked about before. It's for our ideal gas constant, and it's 8.314 joules over K dot mole. So that's my R. I'm going to make that arrow a little more obvious. There we go. T is our temperature in kelvins. Now Q we talked about before. Q is going to be our ratio. It's like KEQ. KEQ was at equilibrium. Q was at whatever conditions we have. So our Q is still the concentration of our products raised to the coefficient over the concentration of our reactants raised to the coefficients. Now it's important to remember that for gases, and we've got this ideal gas constant, for gases, I don't necessarily have concentrations. Sometimes I have pressures. But for a gas, the pressure and the concentration are directly proportional. So instead of using the concentration raised to the coefficient, what I can do is I can take the pressure of my products and raise it to the coefficient over the pressure of my reactants and raise it to the coefficients. So the Q is just like KEQ, but I'm not necessarily at equilibrium, okay? So here's my example. I've got this reaction, H2S plus O2 forms H2O and SO2, and I have to do two things. I want to find out the delta G under standard conditions and the delta G if I'm not standard conditions. What if I have weird pressures for all of these things? Okay, so I'm no longer at 1 atm. So delta G standard, that one's easy. We've done this before. No big deal. I've got my table, I've got my information, so off I go. I've got 2 waters. So water is negative 300.4. I've got 2 sulfur dioxides. SO2 is negative 228.57. I'm going to tally those up, minus my reactants. I've got 2. H2S is negative 33. And then I've got 3 O2s. O2 is 0. Running out of room. Sort of fits. Let's close our parentheses. Okay? So if I tally this up, what I get is I get negative 1057.94 for this side, minus 3 times 0 goes away. So 2 times negative 33 is negative 66.02. So my delta G standard is going to be equal to negative 991.92. My units are kilojoules per mole. Okay? So that gets me my delta G under standard. What about non-standard? Okay? So I said delta G is equal to my standard delta G plus my ideal gas constant times the temperature, big T, Kelvin, times the natural log of Q. Okay? So what I'm going to do first is I calculated my delta G. Well, here's the problem. My delta G is going to be in kilojoules. My R is in joules. So first thing I'm going to do is I'm going to change my delta G standard that I just calculated into joules. So instead of 991 point, I'm going to have 991,920 joules. R is a constant, 8.314 joules over K dot mole. My temperature was 25 degrees Celsius plus 273. I get 298. Then I'm going to take the natural log. Now this is where it gets a little tricky. Okay? It is my products. So I've got water. I've got 0.5 ATM of water. Okay? But that needs to be raised to the power of 2. Okay. My second product is SO2. I've got 0.750 ATM. That is also squared because I have 2 of them. Okay. My products raised to the coefficients over my reactants. H2S is 1 ATM. Now, technically, any power I raise 1 to is going to be the same, but just to make sure that I know what I'm doing, H2S, there are 2 of them. So I'm still going to show that it's squared, even though I realize it doesn't really do anything mathematically. Okay. And then I've got O2. O2, I've got 2 ATMs, and that's going to be raised to the power of 3. Okay. Now at this point, all I have to do is start plugging things into my calculation or into my calculator. So I've got 0.5 squared times 0.750 squared divided by 2 times 2 is 4 times 2 is 6. I need to take the natural log of that. So all of this stuff in the middle I got was 0.0234. So I'm going to take the natural log of that. So I get that this is negative 3.755 times 298 times 8.314 plus my original delta G. So 991,920 plus 8.314, oops, sorry, plus, I need to make sure I use parentheses, 8.314 times 298 times negative 3.755. So I should get that my new delta G is 98216. This, if I kept track of my units, I've got Kelvin canceling out. So I'm going to have joules per mole. Or I could say 982.6 kilojoules per mole, because delta G is normally given to me in kilojoules. Okay, so I went from 991.9 to 982. This is my non-standard conditions, okay?